Okay, good afternoon. Thanks, Arianna, for the nice introduction, and thanks, Mattia, for inviting me today. So, yes, as Arianna said, today I will talk about the galactic nucleus, how it formed, and how it evolved with time through theoretical point of view, through models and body models. Before that, I wanted to show you my career path because it's like a loop. I started in Rome with a PhD, and I wrote a body code there, and did many simulations. Then I moved to Israel. Then I went to Germany. Then I went north. I went to Sweden. And then I went south in France with Marie Curie, and then finally I almost closed the loop. It's a loop plus minus 600 kilometers. I prepared this before. Now I'm in Padova, in the northeast of Italy, not far from here. And now I'm their assistant professor, hopefully becoming associate, if I don't get kicked out. So my field of work is around gravity. So I study dynamics and the effect of gravity on the evolution of different on different systems at different scales. The dynamics in different systems. I studied a bit the solar system, but my main focus are globular clusters and galactic nuclei in the context of galaxies. And today, as I said, I will focus on galactic nuclei with particular attention on the Milky Way center. So just before, I know you all know about galactic nuclei, nuclear cluster, but just a slide to remind you about what nuclear clusters are. So if we look in the universe at a random galaxy, most probably we will see a very bright central source. And this central source, if we look with very much attention to it, it can be resolved in stars. And these are the so-called nuclear star cluster. It's a very dense and compact stellar system, which is observed in different kinds of galaxies. And it can be recognized as an overdensity at the center of the galaxy in the luminosity distribution. Nuclear star clusters, as I said, are present in every kind of galaxy, and they are extremely common. Here you see the occupation fraction as a function of the stellar mass of galaxies. So you see it peaks between 10 to the 8 and 10 to the 10 solar masses in stellar mass, but they are basically everywhere. At larger masses, we have the nuclear cluster is basically replaced by the supermassive black hole, and in this range, nuclear star cluster can coexist with a central supermassive black hole or not. And they are present mostly in more than 70% of the observed galaxies. And these are observational limits because, for example, the bulge can make it difficult to distinguish the nuclear cluster. And they are very compact systems. So, as you know, globular clusters have effective radii of around 10 parsec, while nuclear clusters have effective radii between 2 and 5 parsec. So they are most of the mass of these systems that can reach more than 10 to the 7 solar masses are concentrated in only 2 parsec. As I said, their mass can be between 10 to the 6 and 10 to the 7 solar masses. All concentrated in a few parsec scale. And at the center of the Milky Way, we observe one of these monsters, which is our central nuclear star cluster, which has a mass of 2.5 10 to the 7 solar masses, more or less. And at the center of this nuclear cluster, there is our supermassive black hole, Sagittarius A star, which has a mass of 4 million solar masses, more or less. According to the most recent estimates, and not according to Eugene model.
Well, at this moment in time, yes. Come back in 20 years, we'll talk.
And as Mattia tells us, the nuclear cluster is at the center of a very active region with a lot of things going on. There is a lot of gas. There are stars that orbit around the nuclear cluster. There are massive stellar systems like quintuplet arches, which I don't know, it's over there. And there are clouds of gas, and a lot of is going on. But the nuclear cluster of the Milky Way is sitting, as every nuclear cluster in the universe, is sitting exactly at the center of the galaxy, where the potential well is the deepest, and it contains at the center a supermassive black hole. So you can imagine that this system has dynamics which is extreme. So stars, stellar remnants, whatever is inside, is doing things that we humans cannot observe around us. Let's say like this. And we know that nuclear clusters' properties, for example, their mass, it's scaling with the properties of the galaxy, with the type of galaxy, and also it's correlated with the number of globular clusters, for example. So the properties of nuclear clusters and they are also linked with the mass of the central supermassive black hole if present. So these systems are a bridge seem to be a bridge between the large scale of galaxies and the small scale of galaxies. So this is telling us that maybe nuclear clusters didn't form independently from the evolution of galaxies, but we don't know exactly how this system formed. So as I always show in this kind of presentation, there are two main theories that are trying to explain how this system formed. And one of these is that gas from outside the nuclear cluster or outside the galactic center inflows at the center of a galaxy around a supermassive black hole if present. Yes, this time. So I was saying that this first theory for the formation of the nuclear cluster was simple: gas inflows in star form close to the galactic center, and they slowly accumulate all the mass to form the nuclear cluster. And the second theory, that actually was the first one to be made, is the theory that tells that possibly the nuclear cluster formed through the accretion and merger of dense stellar systems like globular clusters. So these globular clusters orbit the galaxy, but they are very massive and dense, so they survive to the tides of the galaxy, and they are affected by dynamical friction, so they lose energy and angular momentum, arrive to the galactic center, and they merge between each other and form the nuclear cluster. And the first scenario is very difficult to be studied through embodied simulations, but the second one is kind of easy. So it was studied in very different ways, and in my work I studied it for the first time for the Milky Way's nuclear cluster in particular. So I used initial conditions for embodied simulations, where initially I had only the central part of the galaxy without the nuclear cluster. So we only had stars in the so-called nuclear bulge, and the central supermassive black hole, which is here represented by this black dot. And then we put globular clusters around this system on random orbits and let them evolve and decay to the galactic center, because the stars interact with the globular cluster stars, and they give the dynamical friction, and this cluster arrive to the center, accumulate, and form the central nuclear cluster. And you can see this in this movie. This is the first globular cluster, which we put 20 parsec from the galactic center, so very close to it. And then the second one and the third one until around 10 globular clusters. These are very massive ones. They are initially 10 to the 6 solar masses, because and they are very dense, because only this kind of cluster can be affected enough by dynamical friction to arrive to the galactic center in a decent time to form the nuclear cluster. And you see, as time goes on, this is the XY projection, this is the XZ projection, so phase on and edge on. You see that stars accumulate in a sort of cluster, which resembles, at least visually, the nuclear cluster. And these are some snapshots of this simulation. So the clusters, so the first simulation, there are only the stars in the background, which is not represented. Then the globular cluster starts, and then there are these other snapshots where you accumulate this mass, and this is all in the XY projection. So at the end of the model, we had something like 10-ish million solar masses accumulated around the supermassive black hole. And when we studied the property for the first, in the first simulations that we did in 2012, so many years ago, when we studied this system, we didn't find any rotation, because we sampled the orbits of the cluster very uniformly, and it was quite obvious that you don't have any leftover angular momentum in this setup. But in another set of simulations that we did later on, we sampled the orbits randomly, so we don't have any uniform distribution, so they come from all over the space on their orbit, and we found out very different results. So in the first set of simulation, the nuclear star cluster was almost spherical and not rotating, but is in this other set of simulations that we did, it was 3 simulations of these 12 clusters that decay at the center of the galaxy. The situation was a bit different. So in the first column there you see the mass map for this kind of galactic nuclear cluster that forms at the end of the simulation, which was 12 gigayears long. And then you see the velocity map and the velocity dispersion map at the end of the simulation. So after 12 gigayears, after this globular cluster arrived and relaxed at the center. So the first map shows you that the nuclear cluster is not spherical, it's a bit flattened. And the flattening that we find in these simulations is comparable to what is observed really in the nuclear cluster of the Milky Way, which is a flattening ratio of about 0.7, and I think here we have 0.6 flattening ratio. And then in the second column you see the velocity, the line of sight velocity for this cluster, and you see that the blue part is coming toward us and the red part is going toward is going away from us. So this cluster is rotating, and it's rotating quite fast at a peak velocity of around 50 kilometers per second. And of course the velocity dispersion is peaked around the central supermassive black hole. So this is a visual representation, which is kind of similar to the observation they do, the integrated field observations that we obtain with many instruments. And these are instead the radial profiles for these quantities. So in the top you see the line of sight. In the middle panel there is the velocity dispersion, and then the V over sigma. The V over sigma is a parameter that tells you, so if it's around 1, the system is, if it's big, the system is rotationally supported because the velocity is larger than the velocity dispersion. It's significant with respect to the velocity dispersion, otherwise the system is pressure supported because it's the velocity dispersion that is supporting the gravity of the system. And the black points are the data, real data from observations from Feldmayer 2014, and the 2 colored lines are for the simulated nuclear cluster. So the blue lines in particular are from the the data from the model, and the red line is from where we contaminated a bit the model, the mock data, with the stars from the bulge of the bulge of the galaxy. So even when contaminated, the observations and the models overlap quite well, and we didn't impose anything to obtain these results. So these come only from the fact that there is a distribution of stars and the central supermassive black hole that probably has a dynamical effect on the orbits of the cluster. Initially it's dominant, the supermassive black hole is dominant in this process, and then when the mass of the accumulated stars around the black hole becomes larger than the mass of the black hole itself. It dominates the orbit, the final part of the orbit of the decaying globular cluster, torquing it and giving rise to this kind of feature that resembles very well the observations. And here there is a comparison between the one of the models and the observations in terms of velocity map. And as you can see, these are this is the map from Feldmayer. It's the famous one that is always used as a reference. The nuclear cluster of the Milky Way is rotating. The velocity is around 40-50 kilometers per second at the highest, and it's tilted a bit. And in our case, in the simulations, the tilt can be reproduced in the same case, and we also reproduce some substructure at the center. But the most striking thing is that we are obtaining the similar rotation. And this is not so obvious because, as I showed you before, when we sample the orbits uniformly, or we have a lot of globular clusters decaying, the effect is that the net angular momentum of these clusters that are arriving to the center is almost zero. So you don't expect so much rotation. But if this sampling is not uniform, and you have this kind of effect of one orbit affecting the other, then you can reproduce the observed rotation of the nuclear star cluster with only globular clusters.
But why is it the globular cluster distribution? Why is the rotational line with the plane in your
We don't have a plane in a simulation, so the
so
plane
you
is
just rotate it so that it's parallel to the
so
plane.
yeah, the plane is created by the decay of globular clusters. So the flattening, we are
So for you, any direction is equivalent.
Yes.
And then you rotate the
Yes,
model
yes.
because okay.
We do the inertia matrix and we find the but so if the cluster, for example, are decaying from the galactic disk, so they have a preferential the initial distribution, so you expect to be more or less aligned with the Milky Way disk. Then you can have some tilt, because we see here that in some cases,
observation is almost aligned.
yeah, it's 9 degrees difference between the plane of the disk and the rotational plane of the nuclear cluster. And you see that, for example, in the first case, this is the photometric plane, I don't know, and the rotational plane are a bit misaligned.
Is it statistically significant, the misalignment? Or
I think so. I think so, because we did. I'm not 100% sure, but I think it was because these are dynamical the SAS, which is the first author of this paper, did the study through dynamical modeling, like Schwarzschild and stuff like this, to find this misalignment, to reconstruct the orbits and such. So I think it's statistically significant. It's very small, but still there. And in the other cases, there is no. So maybe there was a very polar globular cluster that messed up things there, tilting a bit the orbit. So, and I think in this first simulation there was also a substructure, a polar substructure with remaining stars from this polar decay. So it was one of the last decaying globular cluster. So it disrupted toward the end. So after 12 gigahertz, you still saw some tail of the disrupting cluster in the velocity map. And this is something that is actually observed at the galactic center. Yeah, but as I wrote here, so the latest results about the nuclear cluster, about metallicity of stars in nuclear cluster, seems to point toward very high metallicities, so supersolar. Globular clusters are the lowest metallicity stellar sea. No, not all of them. Yeah, yeah. I was thinking about I mean, if this nuclear cluster is formed through the decay of some cluster, must be something, for example, like Terzan 5, which has a very high metallicity population inside it. So who knows? And maybe they are kind of created through these quintuplet and arches like cluster that form inside it. It's not given that it's globular cluster, because it can be young clusters that formed, or the galactic center is full of gas, which is enriched in a weird way, because you retain most of the supernova gas that explode. You have molecular clouds of any kind, so who knows? So
maybe there is no such a sharp distinction.
yes, exactly. Yeah. So the fact is that most of the stars in nuclear star cluster formed more than 10 gigayears ago. They can forming stars around a supermassive black hole. It's super hard. So maybe that's a contribution of the two. So you form some part through decay of clusters which are not globular cluster but dense stellar systems anyway, and some you form through the gas infall when you're lucky enough to fragment gas around such a massive supermassive black hole. But you actually observe very young stars around the supermassive black hole, and these stars must have formed there because they, if you calculate the time to decay a star cluster, it takes more time than the age of the stars. So the stars, there is the so-called youth paradox. So they cannot come from far away. They must have formed where they are. So
what is the timescale to form the nuclear stellar cluster in the simulation?
So in the simulations, it's in the first set, I think it was very long. It was like 10 billion years, with the last cluster arrived very late. In the second set, I think it was shorter. So it took a few gigayears, and then we let it evolve by relaxation. But observationally, yeah, we had this star formation history that is very strong until 10 gigayears ago. Then it slows down, it has some other peak, and it starts again 1 gigayear ago, and then you have another burst, few hundreds of mega years ago, and then you have these stars that are very close to the galactic center that are very young, of the order of few tens of mega years. So it's a very complex star formation history which are current, people from observational side is trying to reconstruct right now, because right now we have the technology to do that. So, but the point is that we can form nuclear cluster with a combination of these two processes, but we have a clear evidence that there is star formation, and we don't have a clear evidence of decay of stellar clusters. So we need a way to disentangle these processes, and we thought one of these tools could be pulsars. In case we have dense stellar systems, in particular globular clusters, we expect that if the nuclear cluster is formed through the decay of these systems, we expect that the nuclear star cluster should be populated by a lot of pulsars, because globular clusters and dense stellar systems in general are a cradle for the formation of millisecond pulsars, because you have a lot of dynamical interaction, you form binaries, also with neutron stars, and then this binary can interact with other stars, they become harder, and then can form a millisecond pulsar. So you recycle the gas, and you spin up the neutron star, and you form the millisecond pulsar. And these millisecond pulsar, once they are formed, they take a lot of time to slow down and disappear and die. So we expect that if they are, if stellar systems are contributing to the formation of the nuclear cluster, we expect a lot of pulsar to arrive to the galactic center and to have a very precise distribution. And in particular, you expect to have very little number very close to the nuclear cluster, and then this number is increasing as you go out, and then it's the probability to find pulsars increases going out, because what is happening is that you are shredding the cluster as you go more and more as you go closer to the nuclear cluster. So the stars from the globular cluster are lost along the way. So you are distributing these pulsars on a very large radius. While if you are forming the system in situ, you expect maybe to have more pulsars close to the galactic center, where the interaction are stronger, and less as you go outside, because the dynamical interaction become less and less strong. So you have less formation of binaries. This must be involved with many other problems, but maybe with SKA or other radio telescope that will be able to observe this thing, we will be able to say something about this. We still need to resolve the pulsars, which is not super obvious, but it can be a tool, or other stellar remnants, stellar type, stellar population can tell us about the history of the nuclear cluster. And then another thing that we explored recently is the possibility that stars not only interact dynamically, so from far away, but in a nuclear star cluster, but they could also interact physically. So they could interact, exchange mass because they are grazing each other, but also even collide, smash each other, and form a new kind of star. And change the stellar population that are inside the nuclear cluster, because if you have two main sequence stars that collide, they form a new main sequence star probably. If you have a giant star with a main sequence, you might strip the envelope of the giant star, and the giant star doesn't look like a giant star anymore. And this is very interesting in the sense that when you have stars around a supermassive black hole, you expect as a density profile a very steep cusp. So after 12 gigayears of history, this system must be more or less relaxed. And when you have a stellar system around a supermassive black hole, if it's relaxed, it's a so-called Bacol-Wolf cusp. Okay, it can change a bit the slope depending on the stellar kind, stellar type, stellar masses, and whatever. But what you expect is a steep cusp. What you observe in the nuclear cluster, at least for the red giant stars, is a flat core. So you are missing giants. Or in younger populations, you see sort of a cusp, but in the giant you see flat.
So it's still holding, because my understanding is that in more recent years, after correcting for selection,
the problem is less strong than it was in 2012, where you only saw really a zero slope. So now it's getting a bit better, but still there is a missing part. I think in the Schlegel and in the Galactic Nucleus thing, still they see that there are, in the review by Reiner, which was recent, 2019, they were still talking about this problem, the red giant. Yeah, the problem was strong also in the youngest stars before, I mean the not red giant stars, but now there it's solved. But in this population, still we see that it's flatter than the rest. And so one idea was that these collisions that can happen in the nuclear cluster, because they are the densest stellar systems in the universe. They can reach up 10 to the 7 solar masses per parsec cube. So it's more probable than in the solar vicinity that two stars pass close by and really interact physically. They can strip each other envelope, as I said, and can make disappear, for example, the red giant stars, or disappear or appear in another as another kind of stars. So we analyzed my models, trying to combine them with stellar collision code. So we took all the results from the densities, the dynamical evolution of the stars, and combined with Ross-Church code for stellar collisions, and try to understand if the stellar collision can really change the distribution of stellar populations at the galactic center. So first of all, in the center, the collisional probability, which is this lambda parameter, is much higher than outside. You can see it also from this plot that gives you the probability as a function of the distance from the galactic center. So close to the center, you have kind of significant probability that stars can collide. Outside, zero. I mean,
that's for main sequence stars or for giants?
That's for, I think it's assuming that all stars are the same mass, so one solar mass, and just main sequence, I think. It's just basic extrapolation. And then this is before the models. It's just to say that, yes, it's probable that at the center starts if they have one solar mass and one solar radius size and mass, they can really approach each other and collide.
And this probability is per unit time, or?
Maybe for, I think so. Or volume, I think. Could be. It's a, or for star, it's a, the
For
probability.
lifetime of the cluster, like 8 years.
Yeah, probably yes.
Okay.
I can check later
so
on.
0.1 means 10% probability that they interacted during the
Yes,
lifetime
yes,
of the
I think
cluster.
so.
Okay.
So, yeah, but I can check later on. I don't remember. And the result of all this was that, in the case of these models that we ran initially, the change in different magnitude ranges, so for different kind of stars, is not very significant. So initially, the number density of stars is given by the dashed line, and the final number density of stars is given by the solid line. And you see the dashed and the solid almost overlap. So before and after collisions, so without and with collisions, nothing changes. So if you have a nuclear cluster as the one that I formed through these initial models, where you have this cluster that arrive, nothing can change. And at least these kind of collisions are not affecting the stellar populations. But in this case, for all the populations, I had a core. So I was starting with a core, and I was not changing the core, basically. So we thought that new models could be useful, more realistic models based on more recent works on the formation of the nuclear cluster from a semi-analytic point of view could be useful to study again this problem and see if really in a more realistic case collisions can be important. And we run new models. So instead of having this very nice globular cluster, one equal to the other, that arrive at regular times to the galactic center, this time we based initial conditions from the models of Abbas Askar 2022 that were really focused on reproducing the Milky Way's nuclear star cluster. He selected a few models that really were giving as a final result something resembling the Milky Way's nuclear cluster. And the particular thing is that in these models we have different masses for the different globular clusters, and we most importantly have that this globular cluster can have inside an intermediate mass black hole. So at the beginning of the simulation, we don't have a supermassive black hole in this case. So we have just the nuclear bulge, the stars in the galaxy, no supermassive black hole, and then these globular clusters start to arrive to the galactic center. One of them, or maybe two of them, have an intermediate mass black hole, and this intermediate mass black hole starts growing in mass at a given rate. And it reaches 4 million solar mass and then stop. It stays like it is because it reached the mass of Sagittarius A star. And in the meanwhile that the supermassive black hole grows, other globular clusters arrive and form the nuclear star cluster. And we run 3 different cases. The first case is this mass growth case. So we have the supermassive black hole which is brought in by the intermediate mass black hole and starts to grow in mass up to 4 million solar mass. Then we have the intermediate mass black hole that doesn't grow in mass. It arrives and stays there without accreting mass. And another case which is similar to the previous one, where the supermassive black hole is present from the beginning, and then just you have the globular cluster that arrive, the intermediate mass black hole arrives and merges with the central supermassive black hole, and that's it. So we have a very small growth of the supermassive black hole. And then here you have the density profile in 2 cases, one it's rescaled. So as I said, the third case, you have a core at the center, so not interesting for the collisions, as we explained before. But in the case of the mass growth, this time you have the blue line, which is a very steep cusp. So maybe now the stellar collisions are more important than before. In the non-mass growth case, which is the orange line, you still have a core-ish case. And the black line is an exercise that you assume that the orbits are shrinking from due to the analytically due to the presence of the supermassive black hole, which is growing in mass, and you get the black line. So it's similar. So the blue line, this is to explain that the blue line is due to the mass growth. So
adiabatic contraction.
yes, exactly. So you're assuming that you are getting. You're saying that adiabatic contraction, so the presence of the growing supermassive black hole is going from there to there, and then there are some random effects due to the different relaxation of the system that give the small difference between the blue and the black line. And the other case must be very similar to the orange line. And in this case, you have the no collision case. This is only for the black hole growth. The no collision case is the solid line, and when you include collisions, you go from the solid line to the one with markers. I don't know how to say it. So you are actually decreasing the stellar density in different bands. So maybe if you have really a cusp at the galactic center, stellar collisions become so important that can actually destroy your cusp and the probability is higher for red giants because they are larger. So you have more encounters with other stars. So maybe this can be a solution to this problem. It was already put out in the theory, but I think it was not really finding the solution. As I said before, nuclear star clusters are showing the presence of very young stars in the very central parsec, in the central 0.5 parsec of our galaxy. So stars must be formed there, so they cannot arrive from outside. They are really born in situ. And so in this region, you have the central supermassive black hole, and you have the S stars, the famous S stars. The one that the S2 star is the one for which we have the mass of the supermassive black hole with such a high precision. And they are very young. They are between 10 and 50 mega years, and they are inside 0.05 parsec. So these stars are rotating with orbits which are similar to Jupiter orbits, something like that. So S2 is an orbit similar to, so they are extremely close to the supermassive black hole. And then there is a larger distance between this 0.05 and 0.5. There is the young stellar disk, which has a radius of 0.5 parsec, an age of 2.7 mega years, so even younger than the S stars. Has a top heavy mass function, so stars are very massive, like 10-ish solar masses. And then you have as a component, of course, the stars of the nuclear cluster, but you also have another component which was recently found out or confirmed, which is the presence of a cusp of stellar black holes. So in a stellar system, massive stars or massive stellar remnants are doomed to segregate at the center for these dynamical reasons. So they are more massive, they lose their energy, they transmit the energy angular momentum to less massive stars and slowly sink at the center. And stellar black holes are the most massive object. So they, at the galactic center, like in globular clusters as well, they arrive to the center. And observationally, we know that must be around 20,000 stellar black holes in a cusp at the galactic center, around the supermassive black hole. So we explored the easy part of the star formation at the galactic center, not like Mattia does, in a very sophisticated way with hydrocodes and stuff. Well, we did it with embodied codes. So what we could do is take in the nuclear cluster, making it as an analytic potential, put the central supermassive black hole at the center and this cusp of black holes, and then assuming stars form in disks because the gas inflows from something that is rotating and then form something that is rotating, a disk. So we put 5 disks that form in a total time of 500 megayears around this supermassive black hole, and we followed its evolution for this whole 500 megayears, one after the other, differently inclined. So this image is telling you that I'm forming these are all disks but differently inclined.
But these are disks of gas.
No, stars. They are just.
So
Yeah, it's embodied simulation. Sorry, I cannot do.
No, I just understand what you're doing.
Sorry. I have this. I have stars. I have the analytic and nuclear cluster, the cusp of stellar black holes, which are particles, the supermassive black hole, which is the grating is the cusp, which is from 0.05 to 0.5 parsec, in the central supermassive black hole, and then you form this one disk of stuff. You put one disk, which is like a John of stars, which has I don't know how many stars, a number of stars, and then another disk with a random inclination with respect to the first one, which is set in the XY plane basically. And then you put a third one, a fourth one, which is more face-on, and the fifth one. And I'm studying how the different disks, which represent the different stellar generations, interact within each other, and how they affect the mutual evolution. To see if the dynamical evolution of this system is leaving some signature. So if the stellar populations, even after co-evolving for some time, are still showing observationally something that can tell us that they were born in different.
So if they mix or not?
Yes, they mix in the phase space. So spatially and kinematically.
But
So
they all
this
have the same radius initially?
Yes, they are the.
So the only mixing is the angular momentum space.
Yes. So they also mix.
Orbital planes.
Yeah.
Yeah, which is.
Yeah, they. So this maybe it's clearer because you have these stars. They appear magically at the center of the nuclear cluster, and they start co-evolving. What do they have? And we found that these different generations they evolve and co-evolve differently. So as one expects, the youngest clusters, the youngest disk remain more flattened, and they continue rotating, while the oldest populations they rotate less. As you can see, this is the first disk that appears, and this is the last disk that appears. This is the velocity map, like the ones that I showed you before. Less beautiful because I made it and not Sassa. But the first disk this is the same scale, is rotating at a very much lower peak velocity than the fifth disk. So if we have different populations that form at different times, we could maybe observationally see that stars that rotate faster are younger than the ones that are rotating more slowly. And there is another interesting fact. In one of the models that we ran, we had some counter-rotating disk, and the presence of the counter-rotating disk was accelerating the evolution of the stars in the previous disk. So here you have the what is that? The blue and the orange line. This is the cumulative distribution of the inclinations of stars. The blue and the orange are the inclination of a model where there is no counter-rotating disk between 100 and 100 mega a year. So the snapshot at 100 mega a year is the orange one, and 120 mega a year. The distribution are basically the same. In another model, we have the green at 100 mega a year. Then counter-rotating disk appears. So after this disk, this is the inclination of stars in the second disk that appears. Then the third disk appears and it's counter-rotating, and the stars are going here in the from the second disk. Yes.
I have a question. So for the counter-rotating with respect to which?
To the previous disk.
Previous one.
Yeah.
But you still have different angle.
Yes, different inclinations.
So you like measure only one projection of the angular momentum, say the LZ.
Yes. Yeah. With respect to the, so if the LZ is pointing in this hemisphere, they are all correlating. If the LZ is pointing in the other direction, they are counter-rotating.
So just compared to the previous.
Yes. Yeah. So it's this distribution of inclination is going from year to year, so it's becoming much more uniform. So the presence of possibly counter-rotating disks is messing up the evolution, and it's making it faster toward relaxation. So this is also another component we have to take into account when we study star formation and stellar populations at the Galactic Center. Then the last thing I want to talk about, if I may, is the fact that galaxies are merging. And so we are going outside the Milky Way now, more general discussion. So galaxy mergers are very common in the universe. We know also the Milky Way went through some mergers in the past. It's ongoing, the merger with Sagittarius, the brought in M54, which is globular clusters, but also a galactic nucleus. And these mergers can lead to the formation of supermassive black hole binaries, because different galaxies, if it's a major merger, can host a central supermassive black hole. They merge, and this supermassive black hole, especially if the galaxies have a nuclear star cluster, can reach very close distances and become gravitationally bound, and then form the binary and form this kind of systems. So, as I said, if the galaxies that merge have a nuclear cluster, this process is quite fast compared to the case in which the galaxies are not nucleated. So mergers are common, nuclear clusters, supermassive black holes are common, so we expect a lot of supermassive black holes in binaries in the universe. But we only observe a few candidates, which can mean that they are not so common, or that we have the observations cannot detect these supermassive black hole binaries easily. So they are very hard to be really detected. So we asked the question, they are very close to the center, so they are very small separation. So they are very localized in a very small region. But if they come from a nuclear star cluster merger, this nuclear star cluster merger could still show some signature that the nuclear cluster that we observed today was once two nuclear star clusters that merged together, and the properties of the nuclear cluster could be influenced in a sense by the presence of this supermassive black hole binary from the properties of the binary that it's forming, so the masses of the supermassive black hole, the orbits, and so on. So we run simulations of the merger of two nuclear star clusters. So we are not merging globular clusters anymore, but two nuclear star clusters, NSC1 and NSC2, with two central supermassive black holes, and we have different models with different mass ratios between the supermassive black holes, but also different initial separation, different initial angular momenta. And we followed this system until it formed a new nuclear star cluster, and the binary became so hard that it was difficult to follow it anymore because the time step became too small. So actually 20 million year simulation, but the merger happens after 1.5 mega year. Sorry, the formation of the binary happens between 1.5 and 2 mega years, so it's quite fast if the nuclear cluster is present. And this is a plot showing the different cases with different views, which is the mass ratio, different initial distances, and also those two simulations with no supermassive black hole and only one supermassive black hole. And you see that the mass distribution is different. So this is the cumulative mass distribution with the radius from 0 to 100 parsec is different if the supermassive black hole binary is present or not. So the top two lines are for one or two supermassive black hole, the others are for different properties of the supermassive black hole binary. So the distribution of mass, like the galactic in the nuclear cluster that forms, are different for different supermassive black hole binaries, but also in kinematics. This is the line of sight over sigma that I showed you before, so how rotationally supported is the nuclear cluster. And you see that at the center, more or less, all have the same V over sigma, but if you go outside, can be very different depending on the kind of binary, and also if you have or not a binary. So the highest values of the V over sigma are actually obtained if you don't have a supermassive black hole binary. And if you have a supermassive black hole binary, and if the mass ratio is very high, for example, you have lower rotationally supported system going outside. And this is the rotational maps. These are the rotational maps. So in two cases, two simulations. So here you have a mass ratio, I think, of a very low mass ratio, 0.01 between the supermassive black hole, and you see that the system, this is the nuclear star cluster 1, nuclear star cluster 2, and the total, and this is at the end of the simulation. So after 20 mega years, the cluster with the highest supermassive black hole mass is rotating slower than the other one. And here you have a slightly higher mass ratio. The two clusters are rotating in a more similar fashion and giving rise to total rotation like this. So even if you have different mass ratios between the supermassive black hole that are forming the binary, you imprint different rotations on your stellar populations at distances which go farther away. Yeah, here I'm plotting until up to 20 parsec. I was saying also to 100 parsec you see this difference. So maybe in external galaxies with very accurate observation, you could see with stellar population studies, you could see this difference and tell something about the presence or not of a supermassive black hole binary, and even about the mass ratio between the supermassive black holes. And also hypervelocity stars, this is the case of the Milky Way, for example. You could see some difference in the distribution of the distance of stars that are ejected away by the supermassive black hole binary that forms. So in the 5 cases we have, there is a difference in how many hypervelocity stars you form, depending on the binary you form, and what about also the distribution of the distance. And all the hypervelocity stars that you form are really coming from the central 5 parsecs, so they are due really to the interaction between the stars and the, so these are the initial distance. So stars that are central are more probably interacting with the supermassive black hole binary after it forms, and to be scattered away, forming the hypervelocity star. So if we observe this kind of stars, so maybe they are telling us also about the presence of a possible supermassive black hole binary. And then we studied also the orbital distributions of stars in this new nuclear star cluster that forms, and we found that the stars are redistributing among prograde and retrograde stars without doing anything. I mean, they are doing a, I don't know, the definition of prograde and retrograde is given by the angular momentum of one nuclear cluster with respect to the other. So this is up, the merger is happening in this way, but some stars end up rotating in the other way. So, and these are the retrograde stars. And the result is that the prograde stars are rotating very fast, and they are distributed in a disk, while the retrograde stars are rotating slower than the prograde stars, and they are more spherically distributed. And the prograde stars can reach distances closer to the center, while the retrograde stars are distributed at larger distances, and they are less than the prograde stars. This is why the density is a bit lower. And this is the fraction of retrograde stars depending on the model. So the retrograde stars are at the end of the simulation are very different. The fraction of retrograde stars vary with the supermassive black hole binary properties, and in particular with the highest mass ratio, so equal to 1, you have the lowest fraction of retrograde stars. So if you have two supermassive black hole of the same mass, you end up with only 15% of retrograde stars. If you have very different, less similar supermassive black hole, you end up with more retrograde stars. And also the eccentricity of the binary is affected by the presence of by this process, and you end up with lower eccentricities if the supermassive black holes have similar mass. And the dynamics of the system between prograde and retrograde stars is different. I'm showing here the line of sight velocity dispersion. So in a case where we have small initial angular momentum, the two populations, the prograde and the retrograde stars, have very different peak rotational velocity, but also in the wings the wings are similar, but at the center the retrograde stars have very high velocity dispersion, while the prograde stars have much lower velocity dispersion, while when you have more similar velocity mass ratio and also more angular momentum implied in the merger, then you have more similar velocity dispersion between the two populations, even if they have different shapes and different rotations. And this has implications on the gravitational wave side, because prograde orbits have larger inner stable circular orbits, so they can give rise to MRIs, so extreme mass ratio spirals, which are longer because they are infalling from a larger distance, and they give rise to a signal which is longer in time and more easy to detect, so they give rise to a larger rate of these MRIs. Retrograde stars instead, they have smaller inner stable circular orbits, so they infall from a very short distance. The MRI is an event that lasts very shortly and is very difficult to observe, so they give rise in the end to a lower MRI rate, and MRIs are the main target for future instruments like LISA. So the presence, the formation of supermassive black hole binaries and the effect on the prograde and retrograde redistribution of orbits inside nuclear clusters can have a very important effect also on future gravitational wave observations. And yes, the prograde stellar orbits can reach very close to the nucleus, to the supermassive black hole, and this is also a reason why MRIs are more common in the prograde population than in the retrograde population. And so I'm concluding because I destroyed you enough about all this information. Yes, just to summarize, I try to explain that nuclear cluster can be formed through a combination of stellar cluster infall and star formation at the galactic center, and in particular the stellar system infall can reproduce the kinematics of the nuclear cluster as we observe at the galactic center, but in situ star formation is necessary, and if it happens can leave very long-lasting observational signature. And so the conclusion is that to disentangle these two processes we need different tools like the pulsars, but also the combination between kinematics and chemistry, so maybe moons in the future will be the key to understand what's going on. And the stellar collisions are important and can explain why we don't have a cusp in the giants at the galactic center. And the nuclear star cluster structure that we observe in external galaxies can tell us if a galaxy went through a merger and if this merger brought to the formation of a supermassive black hole binary. And that's it. Thank you. Was a bit long.
Thank you, Alessandra. So we can have some questions also online. We start here in person, but also online are welcome. Kari?
Thanks for the presentation. Have you looked at the fraction of retrograde stars? So your previous
Uh-huh.
The first slides you showed some in this simulation.
Yes.
How many form there and in these last simulations as well? Because maybe that could be some sort of.
Yeah, in the first simulations we didn't look at it. In the nuclear star cluster formation,
Yeah.
we never looked at it. Maybe it's interesting.
Because I have a
maybe
paper
for sure
that
it's
shows how clumps and bars
Uh-huh.
drive stars to retrograde motion.
Yes.
So we have these simulations that form these stellar clumps in the first
Yes.
years when the gas is really fractionates and they sink into the center.
Yes.
And I found that for the retrograde populations, the clumps generate this spheroidal distribution,
Mhm.
although stars can get scattered even up to the solar
Yes.
neighborhood. We don't have a supermassive
Really?
black hole, I think. Yeah. Bars also cause the same thing when they're forming, like
Uh-huh.
so the retrograde fraction increase, but the retrograde stars driven by the bar stay within.
Okay.
sort of
Okay. They don't
radius of the
escape
bar.
outside.
Sorry?
They
Yeah,
don't-
they don't escape. But maybe, if you have the scenario where you have the gas coming in first,
Yeah.
maybe you expect a certain amount, maybe it's not even a retrograde population,
Mhm.
maybe it's, as you showed, a counter-rotating population,
Yeah.
which is different, right?
Yes.
So maybe retrograde stars can be one of the diagnostics and help you figure out what was the mechanism.
yeah.
Because if you
That's
have
it.
clusters coming in,
Yes.
they're
You
going to
don't.
scatter
Yeah. Yeah.
everywhere.
Yeah. Of course. Yes.
Uh,
Yeah. We never heard that. I should. Thank you. That's a good suggestion.
There.
Are there other questions?
Also,
Okay, Simpson?
okay. So I'm also curious about the retrograde stars. So in your plot, you show the fraction of retrograde stars as a function of time.
Mm-hmm.
So there's like a big drop. Are this big drop at the time of the encounters?
Wait. Again.
So there's a plot of the fraction of retrograde stars. I think.
This one.
Next, this one.
Yes.
So these drops are at the moment of
The formation. Yeah. This drop at the beginning, the one 2 mega year. This one.
Yes.
So here, the two supermassive black holes are not bound; they are far away.
Mhm.
And then they become bound. You have this drop.
So
so
it
they drop-
normally happens.
Yeah, when
at
the
okay.
supermassive black hole forms. Yeah, it's the cause of this formation is the merger. The merger that happens. So all the supermassive, as I showed you in the beginning, the merger is complete. The supermassive black hole binary forms at around 2 mega years, except for this case, which is a bit different because they are starting from farther away. But let's look at this. So 2 mega years, the supermassive black hole binary forms, and you have this redistribution of orbits due to the scattering, due to the presence of the supermassive black hole binary that messes up with the process, with the orbits of the stars, and gives rise to this retrograde or counter-rotating population.
And also for these stars, before they change to retrograde,
Mm-hmm.
and so before they were prograde.
Yes.
Are
Yes.
there like angular momentum is smaller or? because-
Well, they were not, because in the clusters, so they are not, each cluster is not rotating, okay?
Yeah.
So you have some stars that, 50-50, they are going in one and the
Yeah,
other
yeah.
direction. So maybe, so what was your question? So it's not that you don't
Mhm.
have counter-rotating stars, it's that the orbit is going in this direction, so,
So my question is, are those stars with a smaller angular momentum, they are easily to turn
yeah,
to
I
the
didn't
other
check.
direction?
I didn't check. I should check because it could be that they are more effective if they are in the cluster farther from the center because they are more effective so in some way kinematically or because they are less bound to the modern system.
Because I saw in the galaxy model, embodied model, if the star is with a smaller angular momentum,
Yes.
like more elongated orbit,
Yes.
they are easily to turn the.
Yeah,
direction.
that is true also for if you are a global cluster, you're orbiting the galaxy. If you are probably with your rotation with the circular, the direction of your circular orbit, you are more easily stripped away than stars that are retrograde. So yeah, for sure there is a link, but I haven't checked it. I haven't checked anything. I should have told you
There's
before.
a lot of things.
Okay, that was Daniel.
Would you ask until which separation of the black holes does is the presence of the NSC efficient in driving them closer like that?
I think that it's a this is also a
Like
good
you find a
question.
separation in your simulation.
The separation becomes very small. I mean, they are. I don't know.
So
I
far.
don't have it here, but it's fractional parsec at the
Okay.
end. Until when? Good question.
Always.
I think after they merge, the important thing is the density you reach at the center. So the stars are still very important, but it's no more the the fact that there were two nuclear clusters, but it's how cuspy you are at the center.
Okay.
Okay, Mattia,
Sì,
Alessandra?
thank you.
Yes, so your conclusion is that the nuclear cluster forms partly in situ and partly.
No, the conclusion is not a conclusion because we don't. I mean, I cannot exclude.
But if you had to guess what percentage is one?
Yeah, I would win a Nobel Prize, but I can. I don't know.
What's the range?
I don't know. I could be that only the young stars formed in situ. Then it would be mostly stellar clusters. But do you have enough stellar clusters of such a mass and high metallicity to? I don't know.
But these
Possibly,
clusters,
yeah.
but these clusters, I mean, when they are close, they merge relatively.
Yeah, they are. It's super
quickly,
fast.
but, how long for the clusters that are now in the bulge?
Yeah, it's infinite time. Yeah.
I think none of them would merge. Like,
No,
okay,
the,
so
no, no,
billions
no
of years.
cluster. The ones that we observe today,
No.
no way. There must be something like some 5-10 gigayears ago, maybe. If you are within 1 kiloparsec, then in Hubble time, then you have the chance to reach the center, but you have to be very massive.
Okay.
Also, the bars might affect it. Right?
Yes,
Because
if you are trapped in the bar and you follow the orbit, yeah, it would be interesting to put all the ingredients together and see. But maybe you need something semi-analytic because in body.
And I remember from the review of Nadine that she was concluding that the mergers
Are
is
ve-
more important at low
Yes,
galaxy mass.
yes,
and
but this comes from observation because in dwarf galaxies you see that the nuclear cluster is redder, so it's more compatible with globular clusters in terms of stellar population.
So is the metallicity the main
Yes.
argument?
Redder or blue? I never remember the. Anyways,
Yeah,
it's more
yes.
compatible
More
with.
metal-rich
So-
and
Yeah.
redder.
So if we just look at this general trend, the Milky Way should be more in situ.
More in situ, yes. If you look at the observational papers, they always say 80% at least of the nuclear cluster is formed in situ. The rest,
Could
we-
be,
yeah.
but you don't believe this 80%?
I think it's assuming that the progenitors are globular clusters. If you assume that globular clusters are the progenitor, you don't see globular cluster stars in the nuclear cluster. They are more metal rich. I mean, the most metal rich globular cluster is it's much less metal rich than the sun. So stars that we observe in the nuclear cluster cannot come from globular cluster, most of them. So globular clusters are basically excluded from the picture. But what if they are different kind of clusters?
So did you mean like satellites of the Milky Way, or
Also could also be.
is it possible that they?
Yeah, it could also be that galaxy mergers might
Yeah,
affect.
well, they need to deposit things very close to the center. So
Yeah.
anything, any object that sinks must have very compact to begin with in order to
Yeah.
avoid tidal disruption well before it reaches the central parsec.
You should have deposited something like Omega Centauri, but very close to the center and much more metal rich. And dwarf galaxies that merged with the galaxy were metal poor.
Yeah, and also they would be disrupted.
Yeah.
in material.
So
Hundreds
but
of
the
different
nucleus might
compounds,
have been more
parts,
metal
parts.
rich.
Another thing is that another chemical signature of global clusters is the sodium oxygen.
Yes, you don't
correlation.
see second population stars.
Yeah. Well, there's a sizable fraction of stars that
Yeah.
have this feature, and I think this only exists in the massive enough global clusters, if I remember correctly.
The sodium
Yeah.
oxygen exists
No?
in all
All
clusters.
clusters, okay.
There are few exceptions, but they are very low mass globular clusters, and then you can't toil them on a hand.
Okay.
So the sodium oxygen is mostly ubiquitous.
Okay, but are there any measurements for the C individually?
No, that would be the clear signature of globular cluster stars, but I think it's very difficult to observe. Otherwise, they would have done it already, because it's an ongoing discussion about doing that. And also, they are too meta rich for this kind of anticorrelation to appear, I think.
Okay.
So.
Okay. Are there questions online?
I'm sorry.
Okay, I guess there aren't questions, so we can thank Alessandra again.
Thank you.